Good morning, my students. We're back to CHE 311 Physical Chemistry 2 for the last module, Module 4.1 and Module 4.2. We're starting with Module 4.1, Colligative Properties of Solutions 1. We're going to look at introduction, vapor pressure lowering, freezing point depression. Then we'll look at illustrations and we'll conclude. Now, by introduction, when we talk about ideal solutions, we're talking about solutions that are very, very dilute. Now, we're talking about characteristics of ideal solution. And when we talk about all solutions that behave as ideal solutions, then we are talking about dilute, very dilute solutions. So in a dilute solution, the partial pressure of the solvent follows Raoult's law. Remember, we've done this in 100 level, but we're just trying to move a little higher, a little bit, just up the ladder. But basically, still the same basis, Raoult's law. Consequently, in a dilute solution, the solvent, that is the substance in the highest concentration, is governed by the equation 1. We say that the solvent dissolves the solid, and the solvent is always in excess when compared to the solid. So that's why we say it's highest concentration. And this is in terms of the chemical potential given by equation 1, that is mu1, that is for the solvent, is equal to mu01 plus RT in x1, where x1 is the mole fraction of the solvent. Since in real situation we encounter dilute rather than ideal solutions, this behavior of solvent in a solution is useful in treating the colligative property of a solution. Colligative properties are those properties of a solution which depend on the number of molecules present. It does not depend on the nature of the solid or solvent molecules, but on their number, that is on the concentration of the solid or solvent molecules present. And these properties, these colligative properties include lowering of vapor pressure, elevation of boiling point, depression of freezing point, and osmotic pressure. So we're going to look at these 4 colligative properties. Remember, in 100 level, we also talked about other properties apart from colligative properties: intensive properties, extensive properties, and then colligative properties. The first is lowering of vapor pressure or vapor pressure lowering. The lowering of vapor pressure of a liquid by a non-volatile solid or solid depends only on the number of moles of the solid present. The vapor pressure follows Raoult's law, which is P1 is equal to P1 superscript 0 x1, equation 2. The solid enters this equation only in so much as its mole fraction x2 causes x1, that is the mole fraction of the solvent, to be less than 1, because x1 plus x2 will be equal to 1. The extent of vapor pressure lowering is expressed by equation 3, that is delta P, which is the difference between the pure vapor pressure P0 and the vapor pressure of the solution. So P0 minus P will be equal to x2 multiplied by P0. And we'll simplify, we'll get equation 4. This means that the vapor pressure lowering depends on both the vapor pressure of the solvent and the mole fraction of the solid in solution. Therefore, relative lowering of vapor pressure, delta P over P0, is given by equation 5. That is P0 minus P over P0 is equal to x2. Now, this is another form of Raoult's law. Remember, the first form of Raoult's law is equation 2. So equation 5 is another form of Raoult's law. And it is a colligative property because of its dependence on mole fraction of solids. Of course, remember that X2 is equal to N2 over N1 for very dilute solutions. And what we now remember also that N, which is the number of moles, is the weight divided by the molecular mass. We can then, under very dilute conditions, that N1 is far greater than N2. We'll have equation 7. And equation 7 can be used to find the relative molecular mass of the solid, that is M2. Once we're able to measure relative lowering of vapor pressure. The next is freezing point depression. Now, remember that if the vapor pressure is lowered, an addition of a solid, for example, somebody who is cooking, if you have a water boiling, just ordinary water that is boiling, if you add a salt to that water, the water will stop boiling. That means you will have to heat it to a higher temperature before it starts boiling. So there will be elevation of boiling point. And again, if you have a substance, you add solute, it will reduce or depress the freezing point of that substance. So which means that the phase that separates out on cooling is the pure solvent. Now this depression of freezing point can easily be envisaged if you look at something like Coca-Cola. If you take a Coke, put it in a freezer, and it blocks or solidifies or freezes, when you allow it, to defreeze and you want to drink it, you find out that as long as there are still some, solid particles in it, it gets to a point when you see that that Coke will become colorless and also tasteless. It's no longer tasting like Coke. So you see, you have taken all the solid. The freezing point of the solvent have been depressed. So look at equation 8. If we equate the chemical potentials of the solvent A in both phases, we'll have mu A equilibrium, that is both in our solution and that of the solvent. We'll now apply our chemical potential equation again. It means that mu solution is equal to mu naught 1 plus RT ln x1, equation we made before. If we drop the subscript 1, then we will have the difference between the liquid and the pure solid will be the change in Gibbs free energy on fission. And we equate that, we will now get equation 10. And this equation 10 and also equation 11, which is the same if we look at make Kf the subject, we'll get equation 11 from equation 10, can be used to determine the molar mass of the solid. Of course, it is a colligative property. We have an illustration. The solution of fructose is known to contain that of alpha fructose molecular weight, 1 liter of water. Calculate the vapor pressure lowering. So you can see we have delta P equal to P naught W minus P solution. We have vapor pressure of water, we have vapor pressure of the solid as equal to PW minus delta P. Sorry, that's delta P, not AP. But delta P is equal to P naught W X2. So we can find X2 equal to 0.00564. So we now substitute in delta P equal to P naught W. Already we are given P naught W, vapor pressure of water. When we substitute, we can now get vapor pressure of the solution at 17.52 millimeter mercury. Illustration 2, which is also simple again. Naphthalene, 0.01 kilogram in 1000 kg benzene, lower the freezing point 0.4 K, that is Kelvin. From that of benzene, calculate the enthalpy of fission of 1 mole of benzene. We have our equation, that's equation 10 and equation 11. We substitute, the values are given there. Once we substitute, we're able to get delta H naught fission, which is the enthalpy of fission. Because introduction to colligative properties, vapor pressure lowering, freezing point depression, and then 2 illustrations. Thank you very much for listening. See you in the next module, which is the final module for this class. Thank you very much.